In this next example, we have yet again another example involving a cone, except this time it's a conical tank and we're filling it with water. So it's not sand anymore, it's water, and it's moving into a cone that is sort of with the vertex down, okay? Now, what we have here is we've got a cone with a diameter of 6 meters and the height is 5 meters. I think what I'm going to do here is I'll approach it this way, where I'll draw in the radius and I'll draw in the height. Okay, and what's going to happen is as this cone is being filled with water, the radius versus height of the volume of water will always remain constant, right? So if you imagine that the water level is up to, say, this point right here, okay, then the radius of the surface of the water compared to the height of the water, the depth of the water up to that point, will be similar to the radius of the entire cone divided by the height of the entire cone. Okay, so that will always be constant. So since that's the case, what I can do is I'll just approach it this way, where this is R, this is H, and I can say that R over H will always be proportional to the actual radius of the cone, which, because the diameter is 6 meters, the radius must be 3. And the height is 5, okay? So this radius over height will always be proportional to 3/5, right? So another way to say it is the radius will always be 3/5 of the height. Okay, so that's done. Now what we're going to do is figure out the volume of a cone, or the equation that relates the volume to the radius and the height. So that's done. We did that in the previous example. Again, we want to minimize the number of variables that are being related to each other here. Nowhere in the question do we actually want to figure out the radius or the rate at which the radius is increasing. So I want to get rid of the r. So to get rid of the r, what I'm going to do is from here, I will isolate r. So r is going to be equal to 3h over 5. Okay, and so with that, I can substitute now into this volume formula for r. Okay, and so now I end up with an expression that's only in terms of, or expresses volume only in terms of height. So I've got 1/3 pi times 9h squared over 25 times another h. Cleaning that up, I can reduce, and h squared times h is of course going to be h cubed, so I end up with, looks like it's going to be 3 pi h cubed over 25. With that done, I can go over here, go over here and determine the derivative of both sides in terms of time. So dv dt is equal to, this 3 comes down, and I end up with 9 pi h squared over 25 times dh dt. Okay, and then I just need to sub in values. Now, I'm lucky here because it actually tells me that the height is 2. Well, I shouldn't say that the height is 2, but at the point where they would like us to figure out the rate at which the water level is rising, that point is when the water level reaches exactly 2 meters in depth. Okay, so then I can just sub this in. So let's put in dv dt, which is 1.6 cubic meters per minute. And then I've got 9 times pi times 2 meters is the height, squared divided by 25 times dh dt, which is what we're looking for here. Okay, so then I end up with 1.6 times 25 divided by, now this will be 4 times 9, which is 36 pi, equals dh dt. Okay, let me just make sure that's right. 25 multiplied there, divided by 36 pi. Yeah, that's good. And so dh dt, plug this into my calculator, I end up with 0.354 meters per minute. And that's our answer right there.